So, last time we discussed the residue theorem, well, Taylor expansion, Laurent expansion and residue theorem. Any questions on that? Okay. Okay, if there are no questions, I will continue with the towards the end I mentioned that this residue theorem can be, it's a very powerful tool to evaluate some integrals, definite integrals, not indefinite integrals, but definite integrals where the limits are given, lower limit and upper limits are given. Not all the integrals can be done, but some integrals can be performed using residue theorem, which are, some of them are quite difficult to compute otherwise. Okay. So, in order to do that, to show some examples, first let me prove this Jordan lemma. Okay, so what the statement is the following. So, consider this sort of this semicircle of radius capital R. The semicircle of radius capital R, which means so the angle. So, if you look at any arbitrary point on this here, it will have the length r. This is the origin, and here is the angle theta, right? So, point here z prime will be r times e to the I theta, where theta is between 0 and pi, right? As you go from here to here, it will be 0 to pi. Okay. So, now consider the integral of the following type. You take the integral. So, let me call this path. So, it's not a complete closed contour. It's just open contour from here to there. Okay, it's an open contour. So this. So, I integrate over open contour gamma r of some quantity, some function, let's say f of z prime, and I will explain. I will define the conditions on this, and e to the power of I alpha z prime dz prime, okay, where alpha is a real and positive number. In other words, alpha is greater than 0. Okay, it's a real, and there's no imaginary part. Alpha is a real number. And for f of z, we need to. So, the condition on f is f of z prime so z prime meaning, of course, z prime is r times e to the I theta, right. So, f is a function of r and theta. So, what the statement is that f of r e to the I theta goes to 0 in the limit r goes to infinity uniformly as a function of theta. So what this means is that, of course, r goes to infinity, this goes to 0 means that for any epsilon greater than 0 and r, and there exists some, let's say, what shall I call, r naught, such that there exists some r naught such that r greater than r, for any r greater than r naught, f of r e to the I theta, say modulus, is less than epsilon. Okay. Note, you see the point of uniformly as function of theta means, in general, you see, if you think about this, for each theta, this is some function, right? As I change, it will be some function of capital R. Fix the value of theta, okay? Fix the value of theta, then it will be one particular function of capital R. You change the value of theta, it will in general be a different function of capital R, right? So, if you think of theta as a parameter, so for each theta, it's a, so you can think of this as, write it in this way, some f of r e to the I theta, let's just call it as g theta of r. So, this way of writing, just to make it clear that I am thinking of theta as a parameter, right, and it's a function of capital R. So, this is a function of capital R, but for each theta, it's a different function. Now, so in general, so what we are saying, if you say that this So, we are saying that this goes to 0, right. This goes to 0 as r goes to infinity, which means this also goes to 0 as r goes to infinity. So, of course, this must be true. I mean, this is the statement of that, but in general you would imagine that it is a function of theta, right, because for each theta it is a different function, and for these different functions the fall off rate may be different, right. So, in general you would say that it is a function of theta, but when we say uniformly convergent, it means that you can find a r0 which is independent of theta, where when theta is of course between this range, in this range. Okay. So, that is the statement of this uniformly is converging to 0. Okay. Fine. So, if this condition is satisfied, then the statement that the theorem of Jordan's lemma is that limit, you evaluate this and take the limit r goes to infinity, then that is 0. That is the statement. Okay. It is not difficult to, I mean, I already mentioned last time, it is not difficult to see why that is so, because you see alpha is real and z prime is this, right. Now, z prime is in this part. So, z prime, I can, as I said, it can be written like this. Let us substitute that here. So, you will find, I mean, this is the same as r cosine theta plus r times I sine theta, right, because e to the I theta is cosine theta plus I sine theta. Now, substitute that in, so what is e to the I alpha z prime? Well, this is the same as e to the I alpha r cosine theta, right, and then there is a I and I makes it minus, right. So, you get here minus alpha r sine theta. Okay. Now, the point here is that theta you see is between 0 and pi. In this range sine theta is greater than or equal to 0, right. Remember sine theta, you remember sine theta is greater than or equal to 0 in this range, and of course it is less than or equal to 1, that is 1 is always the upper limit, but whereas sine theta is negative in the region, sine theta will be less than 0 and less than or equal to greater than or equal to minus pi in the range theta between pi and 2 pi, right. This is the sine is positive and the angle is here, and sine is negative and the angle is down there, right, in this part between pi and 2 pi. That is a property of sine. I mean, one way to see that after all sine is this length divided by that length, sorry, this length divided by the hypotenuse, right. Now, in this region this is positive, okay, but whereas down there this becomes negative, okay. So, that is why sine is negative in this, right, but we are interested in this range, this region, right. Here sine is positive, I mean non-negative, right. So, what we have here is, you see, in the r goes to infinity limit, this is a positive quantity, right, assumption, this is also non-negative quantity, right. So, r goes to infinity, there is an exponential suppression, right. So, this is the reason why you expect it to vanish. This is just a phase, so this does not matter. This can only make the cancellation even more strong, right, because the phases cancel each other, they oscillate. This is oscillation, right. So, even ignoring that, you see this is already giving exponential suppression, right. Only thing you have to worry about is that what happens if theta is 0. You see, after all we are integrating from, I mean this, the range is theta equal to 0 to pi, right. In the two endpoints theta equal to 0 and pi, this vanishes, right. So, then there is no exponential suppression, right. So, you have to be a little careful. In other words, in this integral, apart from this very, very small part where theta is close to 0 and theta is close to pi, okay, in this part you may have to be a little careful. But for any finite value of theta up here, there is exponential suppression. So, right. Okay. Okay. So, now let's do it in a more careful way. I mean, this is the intuitive reason why we expect this to vanish. But now let's try to prove it more carefully. You can erase all this, no? You remember alpha is greater than 0. Okay. So, let us just take the absolute value of this quantity. Okay. Let me just call let's just call this this guy sorry. So let's just call this as IR. IR is this integral for a fixed radius r, and what we want to prove is that limit limit r goes to infinity of IR equal to 0. Right? This is the statement. IR is just the result of the integral for a finite r, but then the Jordan's lemma says that r goes to infinity. This integral is 0. Right? This is what. So let's just look at the absolute value of IR. Okay. Well, absolute value of IR will be less than or equal to integral over gamma r of the absolute value of this quantity, right? Which means absolute value of f times absolute value of that, but this I already wrote here. So I take the absolute value of this. The phase gets removed when you take the absolute value. So it is simply e to the power of minus alpha r sine theta. And then you have dz prime. So remember, z prime is that. So what is dz prime? Let's write that also down. Dz prime is I r e to the I theta d theta, right? Because for this contour, r is fixed, only theta is changing. So that's that. So again, I take the absolute value of dz prime. So this phase also gets removed. That I goes out. So then you have just simply r times d theta. And the integral is from 0 to pi. Okay. Now there is something which I don't know whether you know it, that in fact, I mean this integral is very okay. Okay. Already before that I can say the following. So remember, I mean this is of course z prime is r times e to the I theta. Okay. Then we know that for any given epsilon, I mean in other words, for large I mean this is so this again I can take the maximum value of this here. After all, we want to find the upper bound. Okay, the maximum value of this will be some. So let's call it max of f on the circle. How shall I put it? On gamma r, max of f on the gamma r. So maximum value of f when the point is going around, right? But the point here is that this goes to 0. You see, as r goes to infinity. This is a statement of uniform convergence, because where I needed uniform convergence, because you see this I can always make it less than some epsilon, right, for sufficiently large r, and that does not depend on theta. That's the point, right? So I can take it out of the integral. That's what I'm trying to say. So let me put it like this. So this is greater than or equal to some epsilon, okay, for where I'm taking r greater than r0, right? That before I define to you what I meant by this convergence, that it is going to 0. Let me write it again. What are we saying? We are saying f r e to the I theta goes to 0 as r goes to infinity uniformly, right? Uniformly as a function of theta. So what it means? It means that for any epsilon greater than 0, there exists some r naught such that for any r greater than r naught, f r e to the I theta absolute value is less than epsilon, and it's independent of theta. This r naught is independent of theta, right? So just take any capital R which is greater than r naught. After all, eventually we want to take r goes to infinity limit. So just take it greater than r0. Then we are saying that this is less than epsilon. So what we are saying is that this is less than 0 to pi. I mean epsilon is independent of theta. I can take it out. Times e to the integral of e to the minus alpha r sine theta d theta. Times r, sorry, I forgot this r. So r also I can take out because r, I mean I'm integrating only theta. Okay. So this is fine. But now it's difficult to explicitly carry out this integral, right? I mean sine, because it's e to the power of something times sine theta d theta. That's difficult. However, again, we are not really interested in calculating this explicit, I mean the details. We just want to find a upper bound.
Exponential dz prime
Sorry, repeat that again. Here, you're talking. Huh?
When you
yeah, here. You mean this one? Up here? No, here. Okay. I took the absolute value, right? Because we are saying that we are taking the absolute value of IR. Well, this is going to be less than or equal to the integral of the absolute value of the integrand, right? So I just took the absolute value of the integrand. There is this absolute value times the absolute value of e to the I alpha z prime. But absolute value, I mean, this is after all, this is the same as exponential of something plus something is the same as exponential of this thing times exponential of that, right? So this is the same as that. E to the power of this times e to the power of that. Right? But this is a pure phase. So modulus of that is 1, right? Okay. So now but I mean, as I said, we are not interested in really exactly calculating this quantity. All we want is an upper bound. Okay. So now what can I erase here? Maybe I erase this part here. Also, this I can erase. I mean, it's clear. I mean, this already I've written. I can erase this part. Okay. Now there is a statement. I mean, in fact, I will just first of all write it down. There is a bound sin theta is greater than or equal to 2 theta divided by pi when in this range. No, not in that range, in this range, 0 to pi by 2. I should mention that, you see, this is, remember, sin theta has a symmetry. Sine of pi minus theta is equal to sine of theta, right? You remember this formula, trigonometric formula? I mean, if you take the sine here or the sine of pi minus theta is this. If this is pi minus theta, this is theta, right? Then if you try to, oh, this is not very good picture, something like this. Then if you try to compute the sine of pi minus theta, you just draw the perpendicular, right? So this divided by that, but that's the same here. I mean, this perpendicular is going to be equal to that perpendicular, right? So this is sine pi minus theta is equal to sine of theta. So therefore, this integral is the same as I can, because it's even if you reflect around pi by 2, right? If you take the range 0 to pi by 2 and then pi by 2 to pi, but pi by 2 to pi will be the same, will give you the same integral, right? So it just becomes 2 times 0 to pi by 2 integral, right? Is that clear? I mean, all I'm saying is that you write 0 to pi as 0 to pi by 2 plus pi by 2 to pi, right? And now look at the pi by 2 to pi. So I want to compute pi by 2 to pi, so e to the minus alpha sine theta d theta. Okay. Now let's just call redefine theta equal to pi minus theta prime. Write it like this. Change the variable, that is. So when you do that, so this becomes okay. We had to fix the range, but this becomes e to the minus alpha sine of pi minus theta prime. But sine of pi minus theta prime is sine theta prime, right? I just use that fact. So this is the same as sine of theta prime. D theta will give you minus d theta prime. So there is a d theta minus d theta prime, correct? And then let's look at the range. When theta is equal to pi by 2, clearly theta prime is pi by 2, right? So this becomes pi by 2. And when theta is pi, theta prime is 0. So this is pi by 2 to 0, but there is a minus sign. I can remove this minus sign and exchange the lower and upper limit. So this goes out and you just get 0 to pi by 2. But this integral is the same as the original integral. Theta prime is just a dummy variable, right? So this integral is equal to that integral, so it just gives you a factor of 2, right? So I can write it as 2 and make it 0 to pi by 2. Okay. Now the statement here is that in this range 0 to pi by 2, there is this bound. Now let's see how one can prove that. I mean, it's more or less clear and intuitively, because let me draw the picture, plot. Theta, this is theta equal to 0 and theta equal to pi by 2. So Remember, pi is 3.14, etc., right? 3.1. So pi by 2 is something greater than 1, right? Pi by 2 is 1.5 something something. Huh? So it's if this is 1, then pi by 2 is somewhere here. I mean, it's more than 1, even more than 1.5. Okay. Now, if you try to plot at pi by 2, the value of sine theta is 1, right? Sine of pi by 2 is 1. So what is this 2 theta by pi? At theta equal to pi by 2, this is just 1, right? Theta equal to pi by 2 is 1. So this gives you a straight line. If you plot 2 theta, if you plot this is 2 theta by pi. If you plot this function as a function of theta, this is theta here. Theta is in this axis, and I'm plotting right hand side 2 theta by pi. That will be just a straight line. Clearly, it's a straight line because linear in theta. So it's a straight line. And it's connecting 0. At theta equal to 0, it is 0. At theta equal to pi by 2, this is 1. So this is connecting these 2 points. Right? On the other hand, I mean, now look at the slope here. Whatever this angle here, if you compute the tangent of that angle, tan of that angle, is going to be less than 1, right? Because this length is greater than 1.5. That is equal to 1. So tangent tan of this angle will be 1 divided by something greater than 1.5. So it's less than 1. On the other hand, if you compute the slope, I mean, let's look at the slope for this function, sine of theta. Okay. So how do you compute the slope? It's simply d sine theta by d theta, right? That gives you the slope of this function at a given theta, right? So in particular, look at the theta at this is equal to, of course, cosine theta, right? At theta equal to 0, the slope is 1 because cosine 0 is 1. So sine theta starts off at an angle 45 degrees because slope is 1, right? Which is greater than this angle. And then it goes and finally it meets here, right? It comes because at that point sine of theta is 1. Sine of pi by 2 is 1. This is also 1. So they meet together. But throughout in between, sine of theta is going above, right? Now you might wonder, well, how do I know? I mean, okay, I'm just drawing it like this. How do I know? Maybe it goes like this and comes back here. Who knows? Huh? Okay. So let's check that if that is possible. So for that to happen, you see the slope. I mean, slope, you see, cosine theta is decreasing, of course, as you increase theta, right? So at some point it should become negative. For this to happen, the slope, I mean, it has to come down. Slope has to become negative, or let's say not necessarily negative. Perhaps no, maybe even that picture was not so clear. Suppose it goes like that. Slope is always positive, but it starts becoming smaller and smaller, and then it comes. But then it has to eventually arrive here. You see. So in this way of drawing, I've still kept the slope always positive, right? I mean, it's never going in this direction, right? It's increasing, but it's increasing slowly, slower and slower. So you might say it can happen, right? Well, but if that happens, then you see at some point, so the slope is decreasing, right? And now it has become less than right hand side, okay? But then it has to catch up with the right hand side. So at some point the slope must increase again, right? So slope here is decreasing, but at some point slope must increase again, okay? That means if I take the second derivative of the derivative of the slope itself, the second derivative of the slope must vanish at some point, right? d2 sine theta, because I mean here the slope is decreasing, but at some point slope has to increase, right? So I mean all this point the slope is, say, the change of slope is negative because the slope is decreasing, but at some point slope has to start increasing, so change of slope must become positive. So initially it's negative, then at the end it becomes positive. So somewhere it must become 0, right? The change in the slope must become 0 at some point. So which means if I take one more derivative, what do you find? It's just minus sine theta, you see. This does not vanish anywhere in between in the intermediate region, does not vanish anywhere, right. So, it is not possible. Okay. I mean, this is just to prove, but I mean, yeah. I mean, it may not be completely obvious. It's true from the picture that initially it is bigger and finally it arrives there, but we don't know what happens in between, right. But this way you can prove that, I mean, this is always less than or equal to 0. I mean, it's 0 only at the origin. Right? After that, it's all, I mean, but at the beginning, of course, I know this is greater than the right hand side. Okay. So, yeah. So, okay. So, we have this bound. Okay. I mean, I hope you are convinced with that. Now, let us see what happens here. You see, so we are saying sin theta is greater than or equal to 2 theta by pi. So, if I replace this by 2 theta divided by pi, right, I mean, I am saying, this is true. So, e to the power of alpha r sin theta is also greater than or equal to e to the power of alpha r 2 theta by pi, correct, because alpha times r is positive, alpha and r both are positive. So, alpha r sin theta is greater than or equal to alpha r 2 theta by pi, and then therefore, exponential is also, right, because exponential is a monotonic function. Okay. So, therefore, if I take the minus e to the minus alpha r sin theta, this should be less than or equal to e to the minus alpha r 2 theta by pi, right, because this is simply 1 divided by that. Okay. So, I can use this bound now to write this right hand side. So, this is going to be less than or equal to 2 epsilon r 0 to pi by 2 e to the power of minus alpha r 2 theta by pi d theta. Okay. And that integral you can perform immediately, right. This integral gives you, I mean, this is just a e to the power of some constant times r, I mean some constant times theta, e to the power of some constant times theta d theta. So, that is, so the result is, let me just write this down here. So, what we are seeing is that I r is less than 2 epsilon r times, okay, this is minus pi over 2 alpha r, okay, times the e to the power of minus alpha r 2 theta by pi evaluated between pi by 2 and 0, right. You can perform the integral, and this at pi by 2. So, what is this quantity at pi by 2? This cancels, so you just get e to the minus alpha r, and at theta equal to 0, this is 0, so it's minus 1. Huh? So, I mean, this minus I can get rid of that. So the whole thing is, so the whole thing is this becomes less than 2 epsilon r times pi over 2 alpha r times 1 minus e to the alpha minus alpha r, right. So, r cancels, okay, and in r goes to infinity limit, this vanishes. Okay. So, what we are seeing is that r goes to infinity is bounded by 2 epsilon, 2 pi, I mean pi epsilon, by pi epsilon. Okay. But pi epsilon itself is going to 0. Remember, epsilon was the thing, I mean, I could take epsilon as small as I wish as r goes to infinity, right. So, that proves that this whole integral goes to 0. So this as r goes to infinity vanishes. So, I mean, the intuitive way of thinking about it was correct. I mean, it was, I mean, only problem was with the near theta equal to 0 and theta equal to pi, if that could give some some non-trivial contribution. No? But this is actually a rigorous proof that there is really 0. Now, this will be very useful in evaluating many things, many integrals. Incidentally, I mean, you see, this was this entire theorem lemma was proven for alpha greater than 0, right. What happens if alpha is less than 0? Because remember, I mean, our main aim was to make this exponentially suppressed, right? This is a phase, so I don't care about the phase. You want to make this exponentially suppressed as r goes to infinity. Now, suppose alpha was negative. If alpha was negative, then you better choose sine theta also negative, right? That means you must take the lower semicircle, not the upper semicircle, but the lower semicircle. So again, that Jordan's lemma will work. If alpha is negative, then you just have to choose the lower semicircle, not upper semicircle. I mean, this will be again quite important in many applications, particularly in computing Fourier transforms and so on. Okay, so now let me just go to some examples to work out how you can integrate using residue theorem. Okay, I think I saw this. All right. So the first example I just discuss here. So I will just go through maybe some example. Okay, example 1. So the integral is 0 to infinity of x square over x square plus 1 times x square plus 4 dx. You have to integrate this from 0 to infinity. Okay. I mean, this can be done. You don't need all this residue theorem. You just make into partial fractions, and it's not difficult to do it explicitly. But all I'm saying is that I'm going to show you that it's very easy once you use a residue theorem. Okay. Well, first of all, this is 0 to infinity. So think of in the complex plane, I have 0 to infinity, and I have to integrate that. But if I want to, construct some closed contour, it's better to take it from minus infinity to plus infinity, right? But that is fine because this integrand is an even function of x. Yeah? So I can as well write it as 1/2 minus infinity to plus infinity, because it's an even function. So you can do that. Okay. So let's evaluate this integral. So what I will do is that I will just maybe I can. Unfortunately, it's going above. Let me write it right here. I take from minus r to plus r. I evaluate this integral and draw a semicircle around. Right, make a semicircle of radius r. I mean, for this I didn't need the Jordan lemma for this. It's just even without Jordan lemma you can use it. Then, so instead of considering this integral, let's consider this integral over the closed contour. This contour is the whole thing from here to there and then back. Here, comes here. So this is the closed contour. Okay. So if I evaluate this, I mean of this whole thing, z square dz. Just replace x by z. So this is a complex variable. Well, this integral is the same as the 1/2 from minus capital R to plus capital R, x square over x square plus 1, because that part, I mean, this is this part of the contour, dx, plus the integral over the semicircle. The semicircle, this part from here to there, I call it gamma r, semicircle. So gamma r, x square, z square, dz over z square plus 1, z square plus 4, dz. Okay. Now this part of the integral, sorry, I written dz twice. This part of the integral, well, I mean, on this gamma r, z is simply r times e to the I theta, where theta is going from 0 to pi. So now you see this goes like this goes like r square, the z square goes like capital R square, dz goes like capital R. So this numerator goes like capital R cube, right, for large R, whereas denominator, this is r square, this is r square. So in the large R, for the large R you can forget 1 and 4, these are finite numbers. No? So the leading behavior denominator is capital R to the 4, right, whereas numerator goes like capital R cube. So it's clear that in a capital R going to infinity limit, this will vanish. Okay. I mean, I'm saying the numerator goes like capital R cube, denominator goes like capital R to the 4. So the overall it goes like 1 over capital R, right? 1 over capital R times some finite number. But then in the capital R goes to infinity limit, it vanishes because it's 1 divided by capital R, right? So this vanishes as R goes to infinity. Okay. So all we are, so therefore you see this integral, which is what we want to calculate, is in fact equal to this closed contour integral because this vanishes, right? Okay. So now since it's a closed contour integral and this function is analytic, it's only a function of z. There's no z bar here, right? So you can use the residue theorem. Okay. So all you need to do, so the result of this integral is simply equal to 2 pi I times the residue divided by 2 times the residue of these functions z square over z square plus 1 times z square plus 4. Well, residue, but what residues? Residues which are encircled by this contour, right? So residues in the upper half plane, Upper half plane meaning all of this part. Okay. So so we basically we have to look at the poles. Where are the poles of this? This has a pole at z equal to plus minus I, because this vanishes, and this vanishes at z equal to plus minus 2I. So the poles are on the imaginary axis at I, 2I, minus I, and minus 2I. These are the poles. So since we are looking at the residues for the poles which are inside this, the only relevant ones are these two. Okay. So let's compute the. Actually, one can just write it in this way. You see that function. I mean, what is inside this bracket of residue is simply z square times z plus I, z minus I. I mean, this if you open this bracket, I mean, if you multiply, that simply gives you z square plus 1, right? Because just the roots of this z square plus 1. And similarly, z plus 2I, z minus 2I. This is what this thing inside, this residue. So, so you see these are simple poles, first order poles, right? At z equal to I, and z equal to 2I, these are the first order poles. So we can immediately compute the residue, which is simply that formula was one of the formulas. So if I want to compute the residue at z equal to I just multiply by z minus I this function, and then take z goes to I limit, right? So multiply this. Let me just call this, I don't know, g of z. So multiply this z, and then take z equal to I after multiplying. This was for the first order pole, it was very easy. You remember the formula. The general formula involves some derivatives, but for the first order, it becomes simple. Where is it? Yeah, the general formula was residue of some function, say residue of some function g of z at some z naught, was 1 over factorial n minus 1, where assuming that is an nth order pole at z naught. So you see factorial n minus 1 dn minus 1 by dz n minus 1 of z acting on z minus z naught to the power of n times g of z. Evaluated at z naught. This is the general formula for the nth order pole, but here you see it's all first order poles. At z equal to I, there is only this one vanishes, there's nothing else. So there is n is 1, so there's no derivative, this is just 1, so it is simply that. Just multiply by z minus I times this function and evaluate at z equal to I. So what do you find here? So when I multiply by z minus I, this factor goes out, and then I substitute z equal to I. So here is I square, so it's minus 1, and there z equal to I, so this becomes 2I, this factor. This has gone anyway. That is z equal to I, so this is 3I from here, and here you get minus I. That is the full answer from the residue at z equal to I. And similarly, we can also compute at z equal to 2I. Again, it's a first order pole. So residue at z equal to 2I is you multiply by z is equal to, this is equal to z minus 2I times g of z evaluated at z equal to 2I, which is when you multiply, this goes out and then put, so this is 2I square, so minus 4 divided by 2I plus I, so 3I, 2I minus I is I, and 2I plus 2I is 4I. Okay. So that's the, well, we can simplify these expressions. So here you get I square is minus, minus minus plus, but that is I square, so I divided by 6. So this quantity is I divided by 6, whereas this quantity is 4 cancels, I cube is minus I, so I. So this is, have I doing correctly, is minus, let's see, I square is minus, that cancels I, so it's minus, minus 1/3, minus I over 3, right? Is that correct? Is it plus or minus? Have I made a mistake here? Huh? Is okay? Okay, so substitute this here. So we have to compute the, so 2 pi I divided by 2, this is pi I. So the full answer is, there's a pi I times the sum of these two terms, which is I by 6 minus I by 3, which is minus I by 6, so plus, so this becomes pi by 6. So that's the answer for this. That's the answer for the original integral. So we are saying this is pi by 6. I mean, this you could have obtained even without doing this. I mean, it's possible to obtain. I mean, yeah. In fact, maybe it's instructive to see whether the direct calculation also gives you the same answer or not, just to check, double check it. So if I want to compute directly, one way to do is just do a partial fraction here. So let's write, so remember this is 0 to infinity, this half was, I mean the original integral was 0 to infinity. Okay. So let's look at, so we want to write it as sum a divided by x square plus 1 plus b divided by x square plus 4. So let's take the common factor, x square plus 1 times x square plus 4. And then here you get a x square plus 4a, and then here you get plus bx square plus b. And this whole thing is supposed to be equal to x square over x square plus 1 times x square plus 4. So one thing is, I mean, there is no constant term here, right? So b must be equal to minus 4a. So b equal to minus 4a, and then you substitute that. So minus 4a plus a is minus 3a. So minus 3a must be equal to 1. Huh? I mean, so this becomes minus 3a times x square, right? So x square is, so a is minus 1/3, right? And therefore b is 4/3. So b therefore is 4/3 by putting in here. Okay. So let me write it like this. So minus 1/3, and then this is plus 4/3. Minus 1/3 and plus 4/3. So that's what this integral is. And now these integrals you can perform. I mean, in general, if I take an integral x square plus say alpha square, this integral dx, you can perform the following way. Change a variable x equal to alpha tan theta. Okay. Then, I mean, this range is from 0 to infinity. So what happens to the range? So what happens is, so dx is alpha secant square theta d theta, right? D tan theta is sec square theta d theta. So this becomes alpha sec square theta d theta. But this is, you see, this alpha square tan square theta, alpha square comes out as a common factor, and you get tan square theta plus 1, which is also sec square theta. So, sec square theta cancels, and then what about the range? Let us see, when x equal to 0, I can take theta equal to 0, because tan of 0 is 0, right. So, theta is 0, but when x equal to infinity, theta is pi by 2, because tan of pi by 2 is infinity, right. So, this is pi by 2. So, the whole result is, okay, 1 power of alpha cancels, there is a 1 over alpha, and then d theta, theta is a result is simply theta evaluated between pi by 2 and 0, which is pi by 2. This is the answer for that integral. So, now we have to do this integral here, dx 0 to infinity. So, you see the result you can immediately read out. So, it's a minus 1/3 times 1 over x square, integral of 1 over x square plus 1. So, alpha is 1 for this case, right. So, you simply get pi by 2, that is the first term, and the second term is plus 4/3. But now you see you have integrated 1 over x square plus 4. So, alpha is 2, right, 2 square is 4. So, you get here 1/2 times pi by 2. So, the result is minus 1 pi over 6 plus 2, 4 cancels plus 1/3 of pi, which is exactly pi by 6, right. So, you see you get the same answer, just a double check. But okay, here we could do explicitly because it was very simple integral. Some of the integrals are very difficult to do explicitly without using residue theorems. Okay. Okay, this was the first example. Incidentally, I should say, you might wonder, well, what happens? I mean, here I just happen to choose the upper circle, right? I could have also chosen the lower circle, right? Basically, I wanted to close this contour, right? So, I could have closed it this way. There is no problem with that, because even if you had closed it down, it does not matter. The gamma r part would have still vanished, right? But now you are going to pick the residues of these 2 points, right? So, again, please check it, verify that if you had done this, you will choose these 2 residues, but you have to also remember that now the contour is clockwise. You see, previously this contour was counterclockwise. If you choose a clockwise integral, well, that is the same as minus of the counterclockwise. So, you multiply by an extra minus sign to the sum of the residues here. That is the only thing. And check that, please check that, I mean, you get again the same answer. It better give the same answer, otherwise there is something fundamentally wrong in the whole procedure, right. Okay, so that is one. Second problem, let us see, second example. Right, that is so can I erase this part now? I mean, not yet. Okay. For this example, it was either way you could do it, but I will discuss another example where it is crucial. Once the integrand is given, I mean, suppose it had also some e to the I alpha x, right? Suppose it had that, then and let's suppose alpha is positive. Then you see you can only choose this contour, because if you had chosen the down contour, it would have exponentially blown up, right? I mean, you remember, this is alpha is positive. For alpha positive, by Jordan lemma, you can take the upper semicircle, right? But if you had chosen the bottom, the down semicircle, this would have meaningless. That integral would be blowing up. You can't make any conclusion from that in that case. Yeah, but here there was no exponential factor. It was just that. So either way, the gamma r part vanished. Right? Yeah. Sorry? You mean to do like this? Huh? So what do you want to do? Sorry, so let's see. I come here and then after that, go up. No, that is not very useful because, I mean, after all, whatever it, because in fact that will be even worse because then you are going to pass through the singularity, right? That's not. It's going to pass through these are the singular points. No? The integral on the imaginary axis is not even well defined. No? So I mean, so what is your aim? I mean, you want to compute this, right? So you want to deform the but on the other hand, if you want to use residue theorem, you have to have a closed contour, right? Whereas this is open contour, right? So you want to close it, but in some convenient way, right? In some way that whatever extra pieces that you are adding, of course, the most convenient is that if the extra piece that you are adding does not give any contribution to the integral, like here, no, it vanishes. Or maybe it is not possible. In that case, still you might include some path where you can actually calculate the integral. It might happen that the function is such that for some path of the integral, you might explicitly be able to calculate. Okay. In fact, we will see one of the examples of that type a little later. Yeah.
What happens if there's singular
if there is singularity there, I will come to that. Then it's a question of principal value and so on. I will come to that. Actually, that's a, yeah. In fact, I hope I will do it. I will be able to come to that point today. I will try to come to that point. So the examples I'm going to give now are essentially the ones where in the original integral, that original integral was from minus infinity to plus infinity, right? So on that path there was no singularity, right? Then we will come to that. That's a more complicated issue. Right? Okay. The second example is this is a trigonometric function. I want to integrate something like this. So 0 to 2 pi, huh? Yeah, 0 to 2 pi d theta 1 plus a sine theta, where a satisfies the condition a square is greater than or equal to 0 and strictly less than 1. I mean, strictly less than 1, because if it was 1, suppose a was plus or minus 1, say a is equal to minus 1, for example, then this becomes 1 minus sine theta, right, which has a divergence because at theta equal to pi by 2, it blows up, right, and that is along the path, right. So that would be like the situation you are talking about, right. So that's why if a is strictly less than 1, there's no way this can vanish, because modulus of sine theta is always less than or equal to 1, right. So therefore there is no singularity in this path. So we want to calculate this. So in such cases, it is always convenient to use the, I mean, if you remember z, if you write e to the I theta is cosine theta plus I sine theta. Let's call this as z. Okay. Then z inverse, which means 1 over z, is simply e to the minus I theta, which is cosine theta minus I sine theta, because this is the complex conjugate of that. This complex conjugate of that, right? So therefore, sine theta is just subtract the 2 and divide by 2i. So it is simply z minus z inverse over 2i. Okay. And then you see the integral from 0 to 2 pi is the same as the integral over okay, let's come to that a bit. So I can rewrite this. So dz, instead of integrating over theta, I integrate over z. Z is e to the I theta. So dz is simply I e to the I theta d theta. Okay. So let's rewrite this integral. So this is the same as dz. So e to the I theta is z. So dz divided by z times I, right? That is d theta. I mean, this is z. Just divide by iz. So dz over iz is d theta. And then you have here 1 plus a, and then sine theta is this. So 1 over 2i times z minus z inverse, which is the same as z square minus 1 divided by z, right? I mean, here I just take out 1 over z outside. And furthermore, okay, let's also multiply the z inside. So this becomes z here, and that z cancels, right? And also just multiply by 2i. So this becomes 2i, and then this goes so 2i up, right? Okay. So that's the integral we have to compute. And now what is the path in this complex plane? It's clear the path is simply I mean, this is unit circle, right? Its modulus is 1, right? So it's just a unit circle, and I'm integrating over the unit circle of radius. So radius 1 and 0 to 2 pi. So this radius is 1, and integrating over that counterclockwise. Okay. So then we can just work out use the residue theorem. The closed contour. Right. Yeah. Sorry. A 2 pi. There's a 2 pi. No. There's a I cancels. Yeah, this I cancels. So yeah, you get 2 dz over this quantity, which is a z square minus 1 plus 2iz, right? And we have a closed contour integral over the unit circle. So this contour is unit circle. Unit meaning radius 1. Okay. So what I need to do is to just find by residue theorem, it's simply so 2 pi I times 2 times the residue of this quantity, which is 1 over a times z square minus 1 plus 2iz. Okay. At all the possible positions of the singular positions inside the unit circle, right? So we have to first find what are the poles of this. I mean, this is a quadratic object, so it will have 2 zeros, right? The denominator is a quadratic function of z, so it will have 2 zeros. So basically, you have to check whether any 0 is inside the unit circle, right? And then so evaluate. So this is the pole inside the unit circle. That's what the answer is going to be, right? So let's calculate this. So what is this? This is roots are what? Z equal to 1 over 2a, and then you get here, well, yeah, 1 over 2a, and then this is 2i, so minus 2i plus minus square root of square of this, which is minus 4, right? And then the product of these two, which is plus 4a square, correct? I mean the coefficient of z square and the coefficient of the constant, both are a. I mean a and minus a. So product is minus a square, but then there is in the formula there is already a minus, right? So minus minus plus. Yeah. So this becomes 2. The 2 you can take it out, and you get here. Okay, so let's do it step by step. Take out a minus, because remember a square is less than 1, right? I mean, we had written down a square is less than 1, right? So this is smaller than that, so it's better to take out the minus. So this becomes I. So this becomes, from the 4 also you can take out, so it becomes 2. So 2i comes out, so 2 goes out here. So you get here minus, so 1 over a times minus I plus minus I times square root of 1 minus 4 is 1 minus a square. Right? These are the two roots. Have I made a mistake here? Yeah. From this, from here to here, or from here to here? Yes. Okay. You remember the general quadratic equation? If you have, let's say, az square plus bz plus c equal to 0, right? It has two roots which are given by z equal to minus the coefficient of the linear term, which is b. Okay, this whole thing is divided by 2 times the coefficient of z square. Then the numerator is minus b plus minus square root of b square minus 4 times ac. This is the general formula. Right? So now I just use the special case. I mean, here the coefficient of z square is a, so indeed there is a 1 over 2a. The linear term in z is 2i, so b is 2i, right? So I put here minus b, so minus 2i. Then plus minus b square, plus minus square root of b square, but b is 2i, so 2i square is minus 4, that's minus 4. And then you have to take minus 4 times a times c, which means the coefficient of z square and coefficient of 1. So coefficient of z square is a, coefficient of 1 is minus a, so the product is minus a square. So minus a square times minus 4, which is plus 4a square.
Why have you said that the phone is inside the unit?
Yeah, I mean, we have to look at it now. We have to look at this. Yeah. So, yeah, this. Let's see which one is the. First of all, this formula is correct. Yeah, it's correct. Okay. So, I think yeah. So there are two poles. One is, I mean, one is with this sign. So let me take out I divided by a. So one of them is square root of 1 minus a square minus 1, and the other pole is I divided by a, or minus I divided by a, square root of 1 minus a square plus 1. Okay. I mean, it's clear. This, look at this here. I mean, a is less than 1. I mean, modulus of a is less than 1. So you want to look at the modulus of this and see, because which of them is less than 1, which is greater than 1. If you take the modulus of that, okay, minus I, you don't care about it. I modulus is 1. Modulus of a is less than 1. Already the first term, 1 divided by something which is less than 1 is greater than 1, right? And this is a positive quantity. So you're only adding to that. So this number is even bigger than 1. Okay. So this is greater than this modulus is greater than 1. So it's outside the circle. This modulus, on the other hand, one can check it's actually less than 1. Okay. I mean, you can prove that. I mean, just take the modulus and you have to do a little bit of algebra. So let's compute the modulus of this guy. Okay. This is less than 1, right? Because a square is positive and less than 1. So this is some less than 1 number. So it's better to write it as minus 1, put here minus and plus, right? So this is 1 minus something. Okay. Now I take the modulus of this quantity. So we want to check whether 1 over a modulus times the modulus of 1 minus square root of 1 minus a square. But this modulus is the same as 1 minus square root of 1 minus a square, because this is smaller than that, correct? I mean, it was modulus, but this is a positive number anyway. So I don't need to worry about the modulus. Okay. So we want to check whether this is less than 1 or greater than 1. So let's see what, suppose I want to check whether this is true or not. But that's the same statement, is that I can put this up here, right? Because modulus of a is a positive number, so the inequality sign doesn't change. Right? So there's that. And then let's see, is it, how do you prove that? So let me take this on the other side and this on this side, right? So you get here 1 minus modulus a is less than square root of 1 minus modulus a square, which I can write as 1 minus a times 1 plus a, right? After all, 1 minus a square is 1 minus a times 1 plus a. And this is, again, I can write it as square root of 1 minus a square, right? After all, right? So 1 minus a factor I can get rid of from both sides. Okay. So we want to check, is it true or not? But this is of course true. This is less than 1. So square root of this is less than 1. This is greater than 1. Square root of this is greater than 1. So this is indeed true. So this is indeed inside the unit circle, this pole. So actually I could have so let's evaluate this integral, I mean the residue. So I can write this, let me call this as Z1, the root, this is Z1 root and that is Z2. Okay. So of course I can, I mean what it means that this function is the same as 1 over, well, a is, let me take out a, because that's times z minus z1 times z minus z2, correct? This function is that, because after all, I mean I just take out a, okay, so that the coefficient of z square is 1. Okay. Then indeed this must be true, because at z equal to z1 this vanishes, and at z equal to z2 this vanishes, because that's how we constructed z1 and z2. These are the roots of this equation, of that quadratic polynomial. So this is the same as that. Okay. Now what I have to do, I have to take the residue at z equal to z1, right? This is z equal to z1 is the pole which is inside the unit circle. So I have to multiply this by z minus z1 and then take the limit z1 goes to z goes to z1. Correct? That is the that's the residue. So when I multiply, z minus z1 cancels, and then z has to be put to equal to z1. So is that. Huh? So the answer is 1 over a times z1 minus z2. So the full answer is 2 pi I times 2 times 1 over a times z1 minus z2. But what is z1 minus z2? See, let's take the difference between this and that. So when I take the difference, what will cancel? This 1 cancels, right? Is it? Yeah, 1 cancels. So you get here, so this is the same as, okay, 4 pi I over a, and then the difference between these two, this will add up. No, sorry, yeah, 1 cancels and this will add up, right? So z1 minus z2, which is minus minus plus, so 2I over a times square root of 1 minus a square, correct? I mean, I take the difference, this minus that. So the 1 cancels, and this just adds up. This part adds up. So it becomes twice that. Huh? So 2I over a square. So now you can see this cancels. 2I cancels with that to make it 2 pi. So the full answer is this. 2 pi over square root of 1 minus a square. Now, is that correct? Yeah, this is correct. So yeah, so this is one way of, this is a way of computing that original integral. Original integral, I remind you, it was d theta divided by 1 minus a sine theta, 0 to 2 pi. And what we are saying is that this is equal to that. I don't know, I mean, probably it's again possible to do it by, without using residue, I'm not sure, but it should be much more difficult if you try to. Huh? Was it 1 plus a sine theta? 1 plus a sine theta, correct, yeah. But actually, it doesn't matter. Yeah. Yeah. I don't know if there's some simple way of doing it directly without using residue theorem. Maybe there is some clever changes of variables and so on to do it. But this is again an example of how powerful is the residue theorem. Now, yeah. Let me, maybe you could read example 3 by yourself. It's a very straightforward thing, okay? And I will just directly jump to example 4. Because example 3 is a very useful thing, but I mean, I will just leave that. It's a very simple thing. You try to see example 3, which is in page 58. And if you have any question, we can discuss it next time. But I think you shouldn't have any question. But anyway, let me go to the example 4. That's quite interesting, actually. So the example 4, I think I mentioned to you last time a little bit about it. We want to integrate sine x over x dx, 0 to infinity. Okay. So, this is the integral. This integral, I mean, you might wonder what happens at x equal to 0, but there is no problem because there is a sign of x also vanishes. Also at x equal to infinity also there would be, without the sign of x there would be a problem, because this would be the integral of that would be log x, and log x goes to infinity at x as x goes to infinity, but the sin x is oscillating, so it cancels. So this at infinity is also well behaved because of the cancellations. So this is fine. So how we will use the residue theorem? I mean, a direct calculation of that is very difficult. I don't know of any way of directly calculating it. But using residue theorem you can calculate. Okay. So what happened? No. Right. So the idea here is the following. So here is 0, and so let's do the following. Let's consider this integral. I mean, again, the idea is to write sin of x as e to the ix minus e to the minus ix over 2I. After all, sin x is that, right? And then now, of course, the point is that I cannot separate it, right? I mean, I cannot individually consider this integral and that integral. I mean, because I cannot talk about this 0 to infinity to the ix 1 over 2I x dx, this separately. So this minus that I cannot talk about. Huh? I mean, this has no meaning. What I'm saying is this expression has no meaning. Huh? I mean, if I substitute that here, you see, I mean, I cannot separately integrate these two terms because each term is divergent. X goes to infinity, this goes to 1. And there's the 1 over x, right? So each term is divergent. Of course, the fact that the combined thing makes sense, it means that the infinity of this must cancel the infinity of that. But it's a bit difficult to control that, right? I mean, infinity minus infinity, what can you say what it is, right? So the better way to do is the following. After all, I know this integral makes sense, right? So let me just evaluate this at up to some epsilon. I mean, so take a small epsilon here and some capital R. Okay, so instead of taking infinity, take capital R, and then take the limit. Epsilon goes to 0 and capital R goes to infinity. Right? At this level, it is perfectly fine. Right? I mean, this integral was anyway well defined even from 0 to infinity. But let me write it like this, and after doing all the manipulations, then I will take this limit. Okay. So now you see this is becoming epsilon to R, epsilon to R. This is perfectly okay because so long as epsilon is not exactly equal to 0, this integral is finite integral. Similarly, this integral is finite. And now I can add the two things. Okay. But again, remember, this is a trick has been done just because I want to separate these two pieces. If I didn't want to separate, I want to keep it as it is, I didn't need to do this. But if I want to use the residue theorem, it will turn out that I need to split the two integrals separately. Okay. Now, if you look at this part of the integral, I mean, you can again convert it back to this type of integral by just taking x to minus x, right? If you change the variable x to minus x, this becomes e to the plus ix, dx by x remains unchanged because this picks up a minus sign, that picks up a minus sign. But the range, this becomes minus capital R and minus epsilon, and there's a minus sign here, so I can exchange the limit, makes it plus. So basically, these two integrals are the same as e to the ix dx over x of, there's a 1 over 2I, okay, let me keep here 2I, integral from minus r to minus epsilon, which is this integral, plus the integral from epsilon to r. Right? So this is what we are finding. So so in other words, minus r to minus epsilon, this part from here to here, and from this part here to here. And after doing this calculation, then I'm supposed to take epsilon and r epsilon goes to 0, r goes to infinity. Okay. Now I have to choose some path to make it a closed path so that I can use residue theorem. Okay. Notice that here is e to the ix. Okay. So remember the Jordan lemma, e to the I alpha x, where alpha is positive, alpha is 1 in this case, right? So if I close the contour like that, there is no problem, because this part of the integral will vanish by Jordan lemma. Okay? I mean, this is the function f. 1 over x is the function f. Remember, in the Jordan lemma, f times e to the I alpha z. So f is 1 over z. But that, of course, vanishes as r goes to infinity. Right? I mean, z prime, z is r times e to the I theta. So as r goes to infinity, that vanishes. Okay? So it satisfies all the Jordan lemma, the conditions of Jordan lemma. So this part of the integral, I'm guaranteed it is vanishing. Right? But still, it is not a closed contour, because from so I go from here, from epsilon, I go here, come there, come here, and then minus r to minus epsilon. Now, what to do from here to here? It's open, right? So I can close the contour, like, for example, this. Or if I wish, I mean, there are many ways of doing it. Here I have no problem. Here there is no Jordan lemma problem, because here now epsilon is small. It's not large. Jordan lemma was for large radius. This is for small epsilon. So here I'm not going to apply Jordan lemma. At this stage, I can either close like that, or if you wish, I can close like this. Answer better be the same. Okay? In fact, again, that's a double check. You have to check. You can check that answer will be the same. But okay, let's do it this way first, because that's easier. So that's my full contour. So let's call this as a gamma r, this semicircle, and that gamma epsilon. Okay? From here to there. So the full contour I choose, the contour is say minus r to minus epsilon plus the integral over gamma epsilon, which is this integral, plus the integral epsilon to r, and then integral over gamma r. Okay, this is now a closed contour. So I go here, come here, here, and here, come back to this. This is a closed contour. Okay. And I have the integral of the integrand is simply e to the I z over z dz along this contour, 1 over 2i. Okay. Now, so now use residue theorem. So question is there any pole here? There is no pole, right? I mean, the only possible pole is where z equal to 0. So inside here, there is no pole. So this integral is 0 actually by residue theorem. Okay. So that means the sum of these 4 integrals must vanish. Okay. But we already know that gamma r is 0. This is 0 by Jordan lemma. Okay. So that means this integral plus that integral must be equal to minus of that integral. Now, we are interested in calculating this plus that. Right? So what this is saying is that this integral that we are interested in is actually equal to minus the integral over gamma epsilon. This is gamma epsilon, sorry. Minus gamma epsilon of this quantity, 1 over 2i e to the iz over z dz. Okay. So over this circle. So here is an example where you see that in order to make a closed contour, I put this contour, which that was fine, by Jordan lemma it is 0, but this contour is not going to be 0, as we will see. However, even though it is not 0, we can calculate that easily. That's the point. So therefore, we will be able to calculate the original integral, because this integral we can calculate. Okay. Okay. So let's see what is that in this circle. So z is epsilon times e to the I theta. Okay, and theta is going from pi to 0 because it's clockwise. Or if you wish, you can make it 0 to pi and then get rid of this minus sign. Either way. So dz is I epsilon e to the I theta d theta, and then plug that back here. So this becomes minus 1 over 2i. Okay, I keep it at the moment as it is, pi to 0, because that's a path. And then here you have I epsilon e to the I theta d theta. Z is epsilon e to the I theta. And then you have e to the I z, which is e to the power of I epsilon e to the I theta. So, here this epsilon e to the I theta cancels with this, and this I cancels with that, and put the minus sign to make it 0 to pi. So, this integral is 1/2 0 to pi of e to the I epsilon e to the I theta d theta. That's the okay. But of course, to compute exactly, I mean, it will be difficult, but really I am interested in finally epsilon goes to 0 limit, right. So, if epsilon goes to 0 limit, I can expand this exponential, right. So, expanding the integral, the exponential, we find, so that integral, so e to the power of I epsilon e to the I theta is simply 1 plus I epsilon e to the I theta plus and so on, 1/2 I epsilon e to the I theta square and so on, right. And if you integrate it, substitute that and integrate it. So, the first term, so I have to integrate this 1/2 d theta 0 to pi. So, 1/2 of this whole integral d theta 0 to pi. Okay. So, the first term gives me 1/2 times this d theta integral is simply pi. So, pi, okay, the first term. The second term, I mean, is epsilon I epsilon divided by 2, and that integral gives me 1 over I integral of e to the I theta, I mean e to the I theta evaluated between pi and 0, which is -1 minus -1, so it's -2, okay, and so on. You can keep doing it, but the point here is that in epsilon goes to 0 limit, these are all going to vanish. This is first order in epsilon, this epsilon square, all these things. In the epsilon goes to 0 limit, they all vanish, and what you're left is that in the epsilon goes to 0 limit, you simply get pi by 2. Okay. So, that is the result of this integral, is that? Let's see. Right, it's pi by 2 indeed. Huh? So, that integral is pi by 2. Yeah, is that clear? So, you see that tactics here was that we were to make a closed contour, I had to put the big circle which was vanishing by Jordan lemma, but the small circle, it was not vanishing, right. In fact, that is what is giving the final answer, because there was no residue in the inside. But that small circle I can compute, because in the small circle, I mean, I can just make an expansion. Epsilon is small, so I can just make an expansion for small epsilon and just take the leading term, right. So, all these things didn't matter. So, it was doable, that integral. Just if, as I said, I mean, you could have chosen, there are many ways of choosing this contour after all. As I said, here it's this here, this was a 0, this was minus epsilon, plus epsilon, and then here is plus r, minus r. Okay, this part of the thing, it was fixed once I choose this e to the ix. You see, here again I had a choice. You see, I mean, what I did, I converted this to that form by x going to minus x. But I could have, instead of here, take x goes to minus x, and it would have converted here. In that case, you see, you would be doing integral over e to the minus ix. In that case, to apply Jordan lemma, you have to take this lower circle. Okay? But anyway, let me just keep it as it is, but still I have a freedom here. You see, I took this contour here, but suppose I choose this contour, what happens then? I mean, I could have closed like that. Okay. Now you see this gamma epsilon part is I mean, before it was clockwise, now it's counterclockwise. Okay, and you will find if you do the same thing, I mean, this will finally give you minus half pi. I mean, if you just go through the same analysis, okay. You will find that this contribution, so the gamma epsilon contribution gives you minus pi by 2. Okay. But now the residue theorem is not empty. I mean, the right hand side is not, because there is a pole at z equal to 0, right. So, the result of this integral, I mean, minus r to minus epsilon plus epsilon to r will be the 2 pi I times the residue, and then minus the gamma epsilon. So, it will give you just a minus pi by 2. Okay. So, what is the residue at z equal to 0 of which quantity, of this quantity, right. So, this residue we can calculate, this is first order pole e to the I x at z e to the I z over 2 I z at z equal to 0, the first order pole. So, you get, you multiply by z and put z equal to 0, right. So, this simply becomes 1 divided by 2 I times 2 pi I, right. So, that just gives you plus pi. So, this guy is actually plus pi. So, indeed, if you take this, again is equal to pi by 2. So, I mean, again, answer is the same. Of course, it had to be, right. But sometimes these are useful because it may happen that in the various steps you might make some, silly algebraic mistake, So, if you have sufficient time in the exam or something, you could try to calculate a different way and see if the answers are the same, All right, now, so half an hour now. So, now let me just come to the question you are asking, because that's so, I mean, any question here? I mean, after that, I will come to this situation where on the path itself there is a singularity. So, of course, the things not well defined. So, you have to do something. Yeah. The thing is that it is actually quite, it appears a lot in physics, in fact, particularly in the Green's functions and so on. So, it is quite useful to know that, know what you do there. So, let us so consider some integral like this f x over x minus x naught. Integral is from minus infinity to plus infinity, and x naught is real. Everything is real, x and x naught, everything is real, dx. I mean, this integral is clearly not well defined, because here you are integrating, say 0 and say x naught is somewhere. So, this blows up, unless of course it happened that f of x vanishes at x naught, right. In that case it would be fine, but suppose it was not vanishing. So, suppose f of x naught is not 0. In that case this integral is not well defined. Okay. So, what do you do then? I mean, so the trick here is to deform the contour a little bit. So, just you have many ways of deforming. For example, you can deform like that, or you can deform like that, and give a definition of that. I mean, you define it like that. This is like regularizing. You regularize this integral. I mean, it's of course not the original integral, because original integral doesn't make sense. This just blows up. I mean, you cannot make any meaning of the integral. So, what you do is you just deform the contour a little bit. Answers will not be unique. I mean, answer will be different if you choose this path or that path, okay? Because indeed you can see the difference between these two choices is a closed contour encircling this singularity, right. So, the difference will be actually the residue, right. So, the answer will not be the same, but it turns out in physics the choice of this contour that you have to choose, how you deform this contour depends on the particular physics problem. Okay. The physics problem dictates to you how you should deform the contour. Okay. So, I mean, so let me just write it like this. So, I mean, if so let me call this, let's look at this guy. So, I deform the contour like that. So, this integral will become minus infinity to say x naught minus epsilon. Epsilon is some small thing, plus epsilon to infinity, x naught plus epsilon to infinity, okay, plus this small thing, whatever, let's call it gamma epsilon, integral over gamma epsilon, this semicircle. So, you define your integral over whatever the path of this function like that, right. And then of course, you can evaluate this provided you can close contour somehow at infinity, right, and use the residue theorem, etc. You can, to find the poles inside here, you can do that. Now, this quantity, if you take just this part, this is called the principal value. principal value of the integral. So you of the integral. I mean, you take the limit. In the limit, epsilon goes to 0. I mean, you evaluate this and take the limit epsilon goes to 0. That is called the principal value of the integral. Okay. In fact, you can exactly do the same way that we did before, this part of the integral for a small epsilon, because assuming that f is analytic here in this region, with fx naught is not equal to 0, I can make a Taylor expansion, right? So f of say z equal to f of x naught plus z minus x naught f prime, I mean df by dx, df by dz at x naught, and so on, right? And then if I look at this integral on this gamma epsilon, so this integral simply becomes, I mean, you see on this circle z minus x naught is some epsilon times e to the I theta, right, on this semicircle. X naught is the center, so z minus x naught is that. So dz is epsilon I e to the I theta, d theta, and then that guy fz, we want to compute this, right, z minus x naught dz on that gamma epsilon. This is the same as, okay, z minus x naught is that, dz is this. So the ratio of these two gives you I d theta, right? I mean, this divided by that, right? This divided by that. Epsilon e to the I theta cancels, so you just get I d theta. And the integral is from pi to 0, right? And then the f of z, so which is f of x naught, plus z minus x naught is I epsilon, plus order epsilon, right? I mean, all this will go away when epsilon goes to 0 limit. So leading term is just that. So this integral simply gives me I minus I pi f of x naught, minus because integral is from pi to 0. So this part of the integral we already know. It is minus I pi f of x 0. Okay. So if this integral you could, I mean the full contour integral you can do it by, say, by using Jordan lemma, closing the contour up or something, then okay, you will be able to calculate that. In that case, you can compute this principal value. I mean, it will be that and minus this quantity. Of course, if you choose a different path, here, in this case, it will become plus I pi fx0, right? But of course, the contour is not different. This result will also be different, right? But the principal value will remain the same. Okay. Okay, so let me just give an example where the physics, I mean, which appears in physics quite a lot, and that appears in the Green's function actually. I mean, I will not, Green's function we'll discuss in much more detail in the 4th chapter, but let me just explain a little bit what is the motivation for this. You see, typically you find some Green's function which are of the of the following type. So let's take 1 plus 1 dimension, although it's not necessary. Write down the wave equation for 1 plus 1. Are you familiar with the wave equation? Electromagnetic wave equation or something? Okay, the wave equation is basically this. So say you have x and t, x in whatever dimension is, x and t. Okay. As I said, I will talk about 1 dimension for simplicity, although this part is not important. You could increase the dimension. Okay. So you are looking at the equation dt square minus dx square acting on the function of x and t equal to delta function. Delta function, again, probably you have not seen, but it doesn't matter. I mean, I will define this in more definite way in the 3rd chapter. This is called Dirac delta function. Probably some of you know it, some of you don't know it, but I will discuss it anyway in detail. I mean, the important point about the delta function is this thing, dx minus infinity plus infinity is 1. Okay. And furthermore, delta of x minus x naught is 0 when x is not equal to x naught. Okay. So roughly speaking, it's like this. If x naught is, say, this point, then delta function is basically 0 everywhere, right? But here it blows up in such a way that the integral is 1, such that the area is 1, you see. So it's a kind of infinite peak, but keeping the area fixed. Okay, this we'll discuss in much more detail in the third chapter. Okay, it's like a Kronecker delta essentially. You know, I mean, if you take the Kronecker delta, delta ij, this is 1 when I is equal to j, and equal to 0 when I is not equal to j. Okay. So in particular, if I sum over delta ij, but sum over I whatever the range is, 1 to n, whatever the range is, this is always going to be equal to 1, no matter what the value of j is, because in this sum there will be I mean, I will take the value j at one point, right? And when it becomes that, it's equal to 1, and for all other values it is 0. So this is, now think of j as x naught and I as x. Okay. So it's just a generalization of Kronecker delta to when the indices become continuous indices. I mean, here the indices are discrete, right? 1, 2, 3 up to n. But you can think of this as again indices, but now they are continuous indices. So think of this as j, and this is I. So Kronecker delta condition is when I is not equal to j, it is 0. This is 0. That is this condition. Okay. And now the sum becomes integral, because now we are talking about continuous variable. We are summing over all possible values of the index I. That is equivalent to integrating over all possible values of this index, which is x. So what this statement is saying, this statement is analogous to that statement. You see, these are. But anyway, we will discuss it later. I just wanted to motivate why one is looking at it. So if I want to write like this, if I want to solve for something like this, you see, this is called Green's function, by the way. You write the Green's function, you write a Fourier transform of this. So write it as some g p e to the I p x plus I e t. Okay, integrate dp de. Okay, let me see. This is the right variable. Yeah. Okay. So suppose I write this is called a Fourier transform. Again, we'll discuss in detail in the third chapter. But okay, this is called Fourier transform. But let's say I just write an ansatz like this and plug it in. Then you see that this when I apply this dt square minus dx square, dt square will pick up minus e square, because d by dt is appearing here. Every time the derivative d by dt acts there, it is going to bring down I times e, right? So two derivatives will make I e square, which will give you minus e square. So I plug it in here, it will give you minus e square and plus p square, plus p square because there's a minus here, plus p square, okay, times g gpe. Okay, and again, now this you have to take, I mean, accept from me that you can write a Fourier transform for this. Okay, and that Fourier transform is, this is simply equal to just the integral e to the I p x minus x naught. I put x naught equal to 0. I mean, just t naught equal to 0. I mean, that doesn't matter. So e to the I p x plus I e t dp dt, dp de. Up to some 2 pi I factors, which I forget now. There are some 2 pi factors. Okay, there are some factors which I don't remember now. But up to that, it's basically again given by this formula. Okay, so now just equate the two sides. You find that this is equal to basically some 2 pi factors, some 2 pi to some power, which I don't remember. So what we are seeing is that GPE is basically some number, let us just call it 1 for the moment, 1 divided by this quantity. Okay. Now, you plug that back in here. So, and if you can integrate this expression, then you can write down the Green's function, right. So, it is in this context that the integral that I am talking about appears. So, the integral that in particular we are looking at is, so the type of integral we are talking about is this here, dp, and actually first let me discuss that. I will only discuss the dE integral, right? dE integral of p square minus e square. Actually, let me use the same sign that they write here. Yeah, p square minus e square, and then e to the power of, okay, here the convention is minus IE, although it's not so important again, minus IET. Okay, well, if you wish, you can put here minus sign. This doesn't matter. These two derivatives will not see the sign. Okay, so I just do the E integral first. After doing the E integral, then I can do the P integral if I want. dP. But we will focus on just this integral. Okay. But this is part of the problem. It's a part of the step required to construct the Green's function. Okay. So this is the reason why. I mean, this is the importance of that, of this type of integral. This is the kind of integral that we are discussing here. You see, the range of E is of course from minus infinity to plus infinity. All these ranges are minus infinity to plus infinity, P and E. And there's a pole. I mean, E equal to P or plus or minus P. There is a pole here. So this of this type. So on the path itself, there is a pole. So if you look at this now, the line here, we have. So this is the E axis. This is 0, and this is P. This is minus P. Okay. So you have two possible poles, and now you can define you can deform the contours in 4 possible ways. No, you can do it like this, both up, or you can put one of them up, other down. Okay, or you can put this down, that up, and finally you can put both of them down. These 4 definitions give you 4 different Green's functions, okay, and they are all required for physics in different circumstances. One of them is called retarded Green's function, other is called advanced Green's function, and one of them is called, I think, Feynman Green's function. So all of them appear in physics for different purposes. Okay, so they have all I'm saying is that they have a physical meaning. The choice of the contour is a physical meaning. It has to do with the boundary conditions and things like that. But let's see. So how we will evaluate this integral. Okay. Let's try to evaluate these integrals. I mean, choose some contours. I mean, some particular contour, and let's try to evaluate that. So first of all, you can see that if I want to write down some closed contour, I mean, this is still an open contour, right? So in order to make a closed contour, I have to close it at infinity by some semicircle. But which way I should do depends, of course, on the sign of this t, right? So for t positive or t negative, you will have different answers. I mean, different choices you have to make. So for example, let's suppose t is positive. Let's say take t is negative. Okay. Suppose t is negative. In this case, then this becomes a positive, right? I mean, some I times some positive number times e, right? In which case, if you want to apply Jordan lemma, I have to take the upper semicircle. Okay. In fact, let's look at let's call this contour C1. This one is C2. This is C3, and this is C4. Okay. You understand this notation, right? I mean, I'm just saying that this is here is up, here it is down. Okay. Let's put here a point to indicate. So for t negative, I will of course have to, for all contours, I have to always choose upper semicircle to use Jordan lemma, because then that part doesn't give any contribution, it vanishes, right? So now you see for this integral, there is no other pole here. I mean, the only poles are at plus and minus p, right? So by residue theorem, that integral is 0 because there's no pole inside here. If you take the C2, so in this case, the integral over C1 vanishes. Integral over C2, C2 is this one, right? So you see the only pole that this path will capture, okay, I will put it like this here. You see, now let's look at the again. I close the path up. Then what is the pole which is inside the contour? It is this one, right? In this case, it will be this one, right? And in this case, both poles. So then you can just use the residue theorem to compute these guys, these poles. I mean, I will not do it now, but it's clear, right? I hope you can, right? It's a simple pole, so you can just compute the residue in standard way. And so you see that you'll get different answers for these 4 contours. Now what about t? If t is less than 0, if t is greater than 0, in this case I have to close the contour down, because if t is greater than 0, this is a negative number multiplying e, I times a negative number times e. So for Jordan lemma, I should use close the contour down. In this case, the integral over C4 vanishes, right? And these will contribute, but different amounts. I mean, here it will capture this pole, here it will capture that pole, and here you will capture both poles, right? So you get different answers. So in this case in particular, C4 vanishes. These two are called advanced and retarded Green's functions. So here is a kind of boundary condition, imposing some boundary condition that at t negative, say t less than 0, this vanishes and it's only propagating forward. Whereas here t greater than 0, it vanishes. So it's right. But in intermediate, these things appear also they play an important role in physics, particularly in quantum mechanics and so on. I forget now. One of them is called Feynman integral, Feynman Green's function. Okay. So they all have their own role in physics. Yeah. I mean, as I said, the calculation is very simple, right? I mean, the residues are very first order, so it's very trivial, right? Just multiply. For example, if I want to compute this contour, let me just do 1. So this contour will be 2 pi I times the residue at the pole P, right? Because this is closed, this is enclosed. So at residue at E equal to P, so I have to just multiply by E minus P and take the limit E goes to P. So E minus P will cancel this E minus P, so you get here minus 2P. So you get here, this is the same as minus 1 over 2P times 2 pi I, okay, 2 pi I times e to the power of minus I P T. That is this path. So, I mean, these contours are like that, no? And similarly, for C3, you will get this pole and so on and so forth. You can do it. Again, I remind you that this is a common mistake I notice people do. For t greater than 0, I have to close the contour down. Okay? But then it's a clockwise path. So don't forget the minus sign. Okay? Many times I've noticed people just forget about this minus sign. So always remember, whenever it's a counterclockwise, you keep it just 2 pi I times the residue. When it's clockwise, it's minus 2 pi I times the residue.